Hey everyone, and welcome to today's Explainer. I am absolutely thrilled to have you here. Today, we're going to embark on this really fascinating journey. We are taking a beautifully simple but ultimately flawed theoretical model, and we are diving headfirst into the messy, complicated, and wonderful reality of how the physical world actually works. We're going to look closely at real-world gases, and more importantly, we are going to walk step by step through the beautiful mathematics that physicists use to fix our flawed theoretical models. So go ahead and grab your digital notebooks because we're about to break down the famous van der Waals equation. Here is our game plan for today. We'll kick things off with the ideal gas illusion, explore exactly what happens when that ideal fails us, and then tackle the two big fixes. Step 1, the volume correction, and Step 2, the pressure correction. Finally, we'll combine all of that into the van der Waals equation itself. All right, part 1, the ideal gas illusion, macroscopic models versus microscopic truths. For years, we've all kind of lived under this comforting illusion of the ideal gas law, PV equals nRT. To make that math nice and simple, physicists basically pretended that gases were made up of these tiny point masses that take up literally zero space. And on top of that, they assumed there were absolutely zero attractive forces between them. But out here in our messy reality, a real gas is made of molecules that behave more like tiny, rigid spheres. They definitely take up physical space, and they actually pull on each other. So molecular volume and attractive forces, those are the two villains that completely break our ideal model. To actually fix this model, we have to connect two completely different worlds. On one hand, we have macroscopic properties. These are the things we can easily observe and measure, right? Like the overall pressure or temperature of a gas inside a container. But then, on the other hand, we have microscopic properties, the hidden reality of a single individual particle's velocity or position, which we can't observe directly. Statistical mechanics is this incredibly elegant branch of physics that builds a mathematical bridge between the chaotic behavior of those invisible individual molecules and the overall pressure and temperature we can actually measure on the outside. Moving into part 2, when the ideal fails, pushing gases to their limits. So, under everyday normal room conditions, the ideal illusion holds up just fine. But the second we push gases to their extremes, reality bites back hard. If we apply high pressure, we are physically squishing those molecules together into a tiny space. Suddenly, the fact that they are rigid spheres taking up actual volume becomes a really huge problem. And if we drop the temperature, the molecules slow way down. Because they're moving so sluggishly, they spend a lot more time near each other, which allows those hidden intermolecular attractive forces to just completely take over. So under high pressure and low temperature, we absolutely have to abandon our ideal assumptions. Okay, part 3, step 1 of our fix, the volume correction, accounting for those rigid spheres. To really wrap our heads around this volume fix, let's think about a simple shopping analogy from our sources. Imagine you're buying something expensive, say for 1,000 rupees, and you're short by just one single rupee. The shopkeeper is probably going to ignore it, right? It's totally negligible. But if you're buying a tiny matchbox for 5 rupees and you demand a 1 rupee discount, that's ridiculous. It's a huge deal in that context, and it might actually cause a fight. Well, in a massive, uncompressed container, the tiny volume of the gas molecules is just like that 1 rupee out of 1,000. You can completely ignore it. But under high pressure, you literally shrink the container so much that it becomes exactly like the 5 rupee purchase. All of a sudden, the physical space the molecules take up matters immensely, and you just can't ignore it anymore. So how do we mathematically derive the true volume? Well, let's break it down. The ideal model assumes the entire container, which we'll call V, is just completely empty, free space. But we know our reality involves rigid spheres taking up room. If we have n moles of gas, and every single mole takes up a specific measurable volume called B, then those molecules physically occupy a space of n times B, or NB. Therefore, to find the true free volume, the actual empty space available for molecules to bounce around in, we just take the total container volume V and subtract the physical molecular volume NB. Our corrected volume is simply V minus NB. It's an elegant, logical, and physically accurate fix. That brings us to part 4, step 2, the pressure correction, or the invisible pull. All right, we've fixed the volume. Now we have to fix the pressure. And we do this by looking at what we call the pulled runner effect. Picture a gas molecule as a runner racing toward the wall of the container to strike it. That physical strike is what actually creates pressure. But because of those intermolecular forces we talked about, the crowd of molecules behind our runner is actually pulling it backward. Imagine trying to sprint into a wall while 3 people are holding the back of your shirt. Because of this backward pull, the molecule hits the wall with significantly less force. The ultimate result here? The real pressure inside that container is going to be strictly lower than the ideal pressure would predict.
Okay, so conceptually, we know the real pressure drops because the molecules are tugging on each other. But as scientists, we can't just throw our hands up and say, well, it's lower. We have to ask the crucial question. How do we mathematically calculate this exact amount of lost pressure?
Let's walk through the math step by step. First, we establish that the real pressure we measure in the lab equals the theoretical ideal pressure minus some amount of lost pressure. Let's call it P prime. Now, what's causing P prime? It depends on 2 interacting groups of molecules. The concentration of the runner molecules hitting the wall, which is the number of moles N divided by the volume V, and the concentration of the crowd pulling them back, which is also N over V. Because these 2 groups interact with each other, we have to multiply their concentrations together. So N over V times N over V gives us N squared over V squared. Then we multiply this whole thing by a special constant, A, which represents how sticky or attractive that specific gas is. And finally, we have our fix. To calculate the theoretical ideal pressure, we take our measurable real pressure P and add back that lost pressure. So our perfectly corrected pressure term becomes P plus A times N squared over V squared.
And now, part 5, the Vanderwall's equation. This is the climax of our derivation.
We did it. Here it is in all its messy, real-world glory. We take the classic, simple PV equals nRT, and we just substitute in our reality checks. We replace P with our brand new pressure term that mathematically adds back the lost force of attraction. And we replace V with our new free volume term that mathematically subtracts the physical size of the molecules. The result? The Vanderwall's equation. It's a robust mathematical model that finally embraces the messy, sticky, crowded reality of real-world gases. To ground all this abstract math back in physical reality, it's really important to realize that those constants, A and B, are like unique fingerprints for every single gas. Helium, for example, is very close to being an ideal gas. It's tiny, it barely interacts, so its A and B constants are incredibly low. But carbon dioxide? That is a large, sticky molecule. Its A constant for pressure is quite high at 3.592, and its B constant for volume is 0.0427. And water vapor is even stickier than that. Let me show you exactly why this matters with a real numbers example from our physics sources. Imagine you have 5 moles of highly compressed carbon dioxide, and it's trapped in a tiny 1-liter container at 47 degrees Celsius. If you naively use the flawed ideal gas law, the math tells you the pressure in that tank is going to be an explosive 131 atmospheres. But if you do it right and use our new van der Waals equation, factoring in those specific A and B constants, the actual pressure is only 77 atmospheres. That is a massive difference. Relying on the ideal model in a real-world scenario like this wouldn't just be slightly wrong, it could be a complete failure of engineering. Before we wrap up, I want to leave you with this somewhat provocative thought experiment. Think about this. If you make a container infinitely large, the volume V becomes enormous, right? Which means our tiny volume corrections just shrink away to basically nothing. And if you crank the temperature up to be infinitely high, those molecules are zipping around so incredibly fast that they can't possibly hold on to each other, canceling out the pressure correction. In those extreme opposite conditions, our messy, complex, real-world van der Waals equation gracefully collapses right back into the perfect, simple, ideal gas law we started with. Isn't that just mathematically beautiful? Thank you so much for joining me today. Keep asking great questions, and I'll see you in the next explainer.